Alright, section 1.4 talks about the matrix equation. And we dealt with this already. Just gonna have different forms. If A is an m by n matrix, so for each matrix we have a row and column with columns a to the sub 1 through a sub n, they're right there. So keep in mind each of those is a vector. And if x is in R sub n, then the product a times x multiplied by this is 1 by n. This is n by 1. So if you multiply, and multiplication doesn't come up until next chapter, which is kind of odd. But for now, they want us to say, well, look, it's going to be this multiplied by this, x2 multiplied by that. And we should, again, get used to this, even though that's not how it's done in algebra. It says a times x, this. It didn't register. A times x will equal b. That's a vector that is n by 1. If you add those like we've been doing, even though there's a lot of those, kind of like this. When we talked about this, you notice that's only one entry, all of that. So that's kind of what we're talking about. And I'll show that as we do this. We say AX is a linear combination of the columns of A using the corresponding entries of X as weights. Kind of like saying C1 A1 plus C sub 2 A sub 2. Kind of like saying that. They're saying here the weights are really X1, X2, X3. This right here. So let's just make sure things work out. Let me remind you again, this is from algebra, and we will do this in the next chapter. Oddly enough, recall if I wanted to multiply two matrices, if I multiply matrix A and matrix B, if this is n by n, this must be m by anything else. Let's say L. The inners must match. Otherwise, the multiplication is not possible. And the outcome is really a matrix that is n by L. So keep that in mind. Again, those are vectors. So we want to get used to this. And here they say, well, using A, the definition, as in example 1, B, row vector rule for computing AX if the product is undefined, explain why. So they want us to compute the product. Example 1 really talks about the algebraic multiplication, and that's coming up in the next chapter. So for now, if I want to look at number 4 on page 40, if I want to multiply this according to what I see up there, this is going to be 1 times 8, 5 plus 1 times 3, 1 plus 1 times negative 4, 2. And I know how to add those already. That is 8 plus 3 minus 4, that is 7. And 5, 6 plus 2 is 8. Now, that's using this theorem. That's B. If I want to use A, I would say, well, look how this works. This right here is 2 by 3. This right here is 3 by 1. The multiplication is possible. The outcome is a 2 by 1. The outcome is 2 entries, 1 column. To generate the first, I use the first. And you're going to always multiply by those. That's why those must match. So if I multiply 8 times 1 is 8, and you add 3 times 1, that's a 3, plus negative 4 times 1 is a negative 4. And if you take the second row, that's going to generate the second row. 5 times 1 is 5, 1 times 1 is 1, and 2 times 1 is 2, and that will yield 11 minus, that's a 7, and that's an 8. Of course, this is much quicker, but you should get used to this because they're going to use that in a lot of definitions. If I go to number 2, if I really don't pay attention to this part, if I go ahead and say, well, look, what this means, you're going to take 5 times 2, 6, negative 1, and the negative 1 times, there's not another column. You should not jump the gun and try and get this right away. You should really work with figuring out if this is even possible. And this does not match. This is not even possible. You can't multiply those two. The dimensions don't match. Now, use the definition of AX to write the matrix equation as a vector or vice versa. You don't have to work them out. Just write them out. So how does this work? Well, according to what I see up there, it's really saying take negative 2 times vector 1, then take negative 5 times vector 2. Isn't that the definition up there? And that should equal this vector right there. Now, anytime you want to start, you should always do this. This is 2 by 4, and this is, oh boy, forgive me. This is 4 by 2, and this is 2 by 1. So the outcome is 4 by 1 if you're going to multiply. If you combine those, you will get a 4 by 1. Again, we're not solving this. We just want to set them up, nothing more. And there's a good reason for that. How about if they gave us this? Can you go back? So can you go backwards? What would you say this is really saying? Isn't this saying, and this you should like, the first vector, right? Z1, the second vector times Z2, the third vector, Z sub 3, the fourth vector, Z sub 4, and that equals a 430. That's really what that's saying. Now, this is A, this is X, and this is B. Alright? So, one thing to do is to really get acquainted with those. We have to run back and forth non-stop. How about this problem? What are they asking? Write the system first as a vector equation and then as a matrix equation. Okay. First, they want us to write it as a vector equation. As a vector equation, that's simple. That is taking x1 times the first vector plus x2 times the second vector. And that's going to equal 4, 1, 2. So that's a vector equation. If you want to write it as a matrix equation, you're going to simply say it is, let me put it next to it, I don't know, I think that would look better. You would write it as 8, 5, 1, negative 1, 4, negative 3, multiplied by x1, x2, and that should equal a 4, 1, 2. And that's how you write it as a matrix equation. So not that bad of a section, actually. We're not doing much. Just getting acquainted. What is this saying right here? It says, given A and B as in 11 and 12, write the augmented matrix for the linear system, before I do anything, the augmented matrix looks like this. 1, negative 3, 0, 2, negative 1, 5, 1, 2, 3. Again, they don't put that line. I'm going to keep on putting that all throughout. So we did that. AX equal B, we just did. And then they say, then solve the system. If I told you that this really gave me, let's see, if I multiply row 1 by a 3 and add it to row 2, that will be 3, that will be a 0, that will be 6, that will be a 5, that will be 3, that will be a 5, that will be 0, that will be a 1, if I'm not mistaken. And if I multiply row 1 by negative 5, or negative 1 and add it to row 2, I'm sorry, here, multiply row, if I multiply row 2 by negative 1 and add it to row 3, multiply it by negative 1, that will make this a 2 negative. And if I divide this row by 5, that's 0, 1, 1, 1/5. And what if I told you on the last step, I worked it out one more step? You know what, this is fine. Let's go that way. So what can you tell? They're saying, solve the system. How would you solve the system? I'll use backward substitution. That would mean right there that I'm getting x sub 3 to be a 1. Do you see where I'm getting that from? And x sub 2 plus 1 equal negative 1/5. I could have left it like that, really. Or x sub 2 equal negative 6/5. That's positive 1/5. My mistake. So that's negative 4/5. That's why it's good to have your notes handy. What just happened? And if I go to the first equation, that reads x sub 1 minus 2 times that, 8/5, plus 1 equals 0. That means x minus 3/5 equals 0. So x is 1 is 3/5. So what does that mean? That means the solution is actually this vector. And hence, those three are linear combinations of that. Multiply the first vector by 3/5, multiply the second vector by negative 4/5, multiply the third vector by 1, guess what you'll get? So that's a linear combination. That's in the span of those three vectors. Okay, I have a couple of theorems really quick. Again, elaborating. The equation AX equal B has a solution if and only if B is a linear combination of A. What does that mean? That means if and only if it works forward and backward. You could go directly and you could go from linear combination to a solution. If you have an m by m matrix and two vectors in Rn, in the range, C is a scalar, then the following two are always true. You could always do this. Something we're going to need later on to talk about transformation and all of that. Here's a problem. So this is kind of how we're going to see these problems. Let U be this vector. Let A be this matrix. Is this a subset of the span of the columns of this vector? Well, the columns of that vector are really vectors. That's like A sub 1, if you remember, A sub 2. So what are they really asking us? They're asking, basically, if this is in the span, it should be a solution to the following. So this is really how it's written. They're saying, can you find C1 times 501 plus C2 times 813 plus C sub 3 times 7 negative 10 to equal 2 negative 32. That's really the definition. If you could find C1, C2, C3 so that I multiply the first vector by this value, by this weight, and I get these three numbers, then it is a subset, meaning it's in the span. Otherwise, it's not. An easier way of doing that is for me just to use augmented matrix. And here I'm just going to go for assume we did this, and we're not after the busy calculation. If I was to tell you that this is what I got, when I simplified, I got 1, 3, 0, and a 2. 0, 1, -1, and -3. And I got 0, 0, 0, and -29. What does that tell you? This last row says 0 times x sub 3 equal -29. 0 equal -29. That tells you there's no solution. What does that mean? That means u is not a subset of matrix A how did they put, oh, subset of the spanned columns of matrix A. And our homework is 1 through 15.